Now, you've seen this before, we kind of looked at it. Probably about as we were one time, people wanted to look at it. Gives us a fairly good review of the main topics. I'm going to go through, comment on it. If there's something you want me to stop and talk more about, let me know. Okay? Okay, so start with vectors, dot product, cross product. Even if you want me to talk about those, I'm not gonna, that's pretty helpful. Okay, projections. You gotta know this picture. You gotta know what a projection is. If you memorize the formula and use the formula, you're not gonna have any insight into what you've got, although, you know, if you're lucky, you might get the right answer. And of course, I'm all for that, you know. I respect luck, and I give credit for it. But of course, if I ask for a picture of the explanation why the projection does what it does, then I better be prepared to draw the picture. You give me the explanation, and I might well do that. That's really important. Projections are very fundamental, as I think you should understand now, having been through the course. Okay. And it's very simple. It's just a right triangle up here. And if you take the fact that B dot W equals magnitude of B magnitude of W times the cosine of theta, you see that this is magnitude of B cosine theta. And you put all that together and you get this formula for projection. Okay. Now the magnitude of B cosine theta is B dot W divided by the magnitude of W. That's just very straightforward. That's algebra 2, algebra 1. Okay. But putting it in this context, yeah, that makes it even more challenging. Can't understand this. And I like the W over magnitude of W, which is a unit vector, instead of putting the W squared here, which makes it look like somehow this thing's inversely proportional to the square of the magnitude of W, which is not the case. Okay, I prefer this arrangement. The other obscures what's going on. It obscures the fact that you're just taking something this long and multiplying it by a unit vector. This thing is here. This is a unit vector in this direction. You multiply a unit vector by its magnitude and you get a vector. Now, this isn't just a magnitude because it could be negative. B to W could be negative, so I'm being a little loose with the terminology. That's a fundamental thing. You gotta know that. Now, plane through a given point perpendicular to a given vector. There's a picture for that. And let's see if that. I've got plenty of light. So. Mostly two boards, but so I'm gonna just do a very short time out. In case I want to write, I'll come back and write something about this. Boards dry. Okay. End of the semester, I don't have to worry about making the board as clean as possible. Things reasonably clean. All right. After fries. Okay. There's a picture that goes with this. You should know the picture. You got a point, you got a normal vector, and you got a vector in the plane. Vector goes from x naught, y naught, z naught to x, y, z. It's got to be perpendicular to the normal vector, and that's all this says. Okay, I'll come back and draw that picture, but a vector from x naught, y naught, z naught to x, y, z is x minus x naught I. That's why you can read it. There's a bit, well, you probably can't. It's x minus x naught I plus y minus y naught k plus z minus z naught k. That's a vector from here to point on the plane. It's got to be perpendicular to the normal vector because that's what it means for the plane to be perpendicular. That's what it means for the normal vector to be normal to the plane. Okay. And then if you do a line through x naught, y naught, z naught parallel to the V, that just means that you're vector from x naught to x, y, x naught, y naught, z naught to x, y, z is a multiple of v, scalar multiple of v. That's all there is to it. Those are your premises. You don't need to memorize fancy formulas if you can work from a simple premise. Okay? Now it's up to your choice. You know, you want to memorize all these formulas and get them confused and mess up, that's okay. Or if you memorize them and don't mess up, that's even better. Okay? But you're less likely to mess up if you know where the formulas come from. Okay, now, of course, not drawing up yet, I'll draw that. A path in space can be described parametrically by an R of t vector. Where R of t is x of t I plus y of t j plus z of t k. Okay. Simple. T is interpreted as time, and your point in space is, or your coordinates are understood to specify a point in space. Then this is a position function, and here's your corresponding velocity function. Just take its derivative. And the derivative is what? It's the derivative of x times I, derivative of y times k, derivative of z times k. In other words, your motion is in one direction is independent of your motion in another. Okay, so R prime is then in your direction of motion. If you make it into a unit vector by dividing by its magnitude, you get the unit tangent vector. Okay, that's all we got to say there. Unit tangent vector. Okay, well, the derivative of the unit tangent vector is normal to the unit tangent vector. Okay, and I just said normal. I left the word normal floating in space there. It's actually normal to the curve. Right, by this function. Because the unit tangent vector is in the direction, the derivative of a unit vector is perpendicular to the unit vector by the isosceles triangle that I talked about back the first time we looked at this. Okay, and that's a standard derivation. Everybody should know that. Okay. So if you want to know more about that, make yourself a note and ask me. Probably won't have time to go over here. A unit normal then just divide the derivative of the tangent vector, which is normal, by the magnitude of that derivative. Now, unit tangent vector is a unit vector. That doesn't mean it's derivative. Unit tangent vector can be changing slowly in time, or it can be changing quickly in time. Okay, or space. Because of course you parameterize this thing into space too. Okay. R double prime is your acceleration if your parameter is time. And I can say if your parameter is time. More specific. You project the unit tangent vector onto RW prime, R double prime, or you project the R double prime onto the unit tangent vector, then you get the tangential component of R double prime because of projection is what it tells you. Okay. So your unit tangent vector gives you the direction. Your R double prime might be like this. You'll have a component in this direction. Okay. Maybe the component is zero. If you're moving at constant velocity, constant speed on a circle, then your tangential component of R double prime is going to be zero. You're not speeding up along that circle. You're not speeding up in the direction of motion, but you are accelerating perpendicular to the direction of motion centripetally. Okay. R double prime minus this projection. Well, here's R double prime. Sorry, here's R double prime. Here's your projection of R double prime on the unit tangent vector. Here's R prime. Here's the unit tangent vector. And I've got this labeled as R double prime. Oh, okay, there we go. R double prime parallel. Okay, that's another notation. R double prime parallel to your direction of motion. And then R double prime perpendicular, where you just subtract R double prime parallel from R double prime. Here's the negative R double prime parallel, and that leaves you with R double prime perpendicular. Okay? You want to have that picture, you want to understand that. I mentioned there's the osculating circle in the plane. And you take the this component, which gives you like a centripetal acceleration, and your speed, which gives you your speed. Okay, your centripetal acceleration is like v squared over r, and you put that together, and you can get the radius of your osculating circle, and it's in the direction of your perpendicular component, because that would be centripetal. Okay. So I'm not going to ask you to do that, unless I want to put an extra problem on there to challenge you. And that label it as a challenge, an optional challenge. Okay. It's something I like to do, but in a weird semester, we haven't been able to do everything, and my brain's been a little bit off in the last month. Yeah, you probably didn't notice the difference. Okay, now, you also have your binormal vector, and we described that in terms of flying. Okay, it just takes a cross product of unit tangent, unit normal vectors, and you have the binormal vector. And now you know if your binormal vector is changing, it tells it the guts and yaw, stuff like that. Okay. So you carry this coordinate system around with you. Okay, and within that coordinate system, you can do a lot of analysis. Okay. Well, we move to quadratic surfaces. Quadratic surface. Here's your general. Now it's not quite your general quadratic form, because you don't have any XYs or XZs or YZs. Okay. We saw a little bit of that last time when I talked about that one Stokes theorem. Choose a slightly different plane. Anyhow, there it is. But this form, which is not again your general quadratic form, okay, but all the XZs and YZs and XYs rotate the thing in space. That's complicated. Okay, I'd love to do it, but it's kind of outside the scope of most calculus. Go to MIT, go to Stanford, that probably do it. Okay. I don't think Tech does. Could be wrong. So, okay. You can generalize this, you can transform this so that the origin of your coordinate system shifts to the point X, Y, Z. That's or HKP. Okay. That's just a transformation. And this is what you get if you complete the square on AX squared plus BX, on CY squared plus DY, on EZ squared plus FZ. And you know, I've had that mistake up there for however many years. This thing's been up. That should be a C there, because the coefficient of Y squared is clearly going to be C, right? Expand this, you're going to get a Y squared, or better multiply C. It's going to be equivalent to this, and this ought to be E. Okay. Notice that AC and D are all non-zeros. AC and E would all be non-zero. So got a couple of typos in there. Wasn't even typed. Okay, so okay, so all three of these are non-zero. You have an ellipse. assuming they're all positive. And of course, I said, if they're all positive, you have an ellipsoid, otherwise you have hyperboloid, maybe one sheet, maybe two sheets. You can tell a lot by the intersection with the three intersections with the three coordinate planes. You can also intersect one of these things with a plane like x equals 5. Okay. You just let x equal 5, replace x by 5, and you get the intersection with the plane x equals 5, and you're going to get some other hyperbolic ellipse. Okay. Or if one of these might not be 0, or two of them, maybe a parabola. Okay. Now, if these aren't 0, you ain't getting, if all three of these are 0, you're not getting a parabola. You get any ellipses and hyperbolas. So sort that out. Okay. I also showed you how to draw hyperbolas and ellipses. Seen anybody actually do it. It's kind of a handy way to do it. Okay. So I'll review that. It's just, if your semi-axes are A in this direction and B in this direction, then there's your semi-axis and there's your semi-axis. If it's an ellipse, it fits within the rectangle. If it's hyperbola, then you have the diagonal lines here that are asymptotes, and the vertices are here, 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 or here and here, depending on which type of hyperbola you have. Not which type, but whether you can have, if you can't have y equals 0, then you're going to have these. Y equals 0 leads you to a contradiction, which would be the square of something is negative, then you're going to get this. And you need to sort that out if you haven't already. And that's actually pre-calculus. It's actually, wait a minute now. That's still covering pre-calculus, there's and calculus too. Done some weird things with the correction, but anyhow, it's okay. Anyhow, then arc length and curvature. Don't think I've said too much about that, but let me see. I can here. Should be obvious. Ratio approximation. So we can talk a little bit about that, but arc length is basically, you're just integrating the magnitude of r prime between 2 points. Because r prime is like how quickly you're moving between those points. Okay, you integrate that over time, it tells you how far you've moved. But the magnitude of r prime, not the vector r prime. Okay, magnitude of r prime is how fast. So it's just how fast, integrate how fast. So for arc length, integrate magnitude of r prime. Yeah, the formula for that was square root x prime squared plus y prime squared, and plus z prime squared if you're 3 dimensions. Okay, and you got to parameterize and all that stuff, which you ought to be getting pretty good at after all the stuff we've done. Okay. Then curvature is just basically how fast the unit tangent vector is changing divided by how fast you're going. Because faster you're going, the faster your unit tangent vector in time is going to change, right? If you want to know how quickly it changes with distance, you correct that for how fast you're moving. So that's just an idea that you probably ought to sort out with the formulas. You'll understand it. So I'm not going to say too much. And any of the stuff you want me to write down more about, or anything, you know, if you do happen to review this video and have a question on it, email me. I can do another video. I can email you back. A simple answer. Next week, all exams will be in the testing center. I'll have nothing to do, be here for office hours. Okay, if you want to come along and keep me awake, that would be fine. If you have, if that would be useful to you. Otherwise, you know, if I get emails, I want people to do it. all those options are, could email me back. That's what I'll be doing, and I won't be here for all that many hours, because we got a lot of other stuff to do. But even when I'm off campus doing other stuff, I check email. Just especially during the first few days of the exam. So I'll just leave it. Okay, so anyhow, okay, now talk about functions of more than one variable. Okay, and of course, logarithm surfaces can represent functions more than one variable. So you've already kind of seen examples of that by messing with quadratic surfaces. But more generally, if z equals f of x, y, then x, y is a function of two variables. I don't have to explain to you what that is. You've been dealing with them since September. Okay, you get a three-dimensional graph. Now, this picture I think is really important. You cut the three-dimensional graph, z equals f of x, y. All the points x, y down here in the plane, every point gives you z. You put all that together, you get a surface. Hopefully everything's continuous and differentiable, so it's nice and smooth. Okay, but if not, you deal with that, and you be aware of it. So if you cut this with a plane parallel to the YZ plane, a plane where x is constant, then you get this, I guess that's kind of greenish shaded plane here, and you get this curve where that plane intersects your surface. Okay, so here's your curve. If you cut with a plane parallel to the XZ plane where y equals constant, then you get this kind of blue shaded figure with this curve. Okay. At the point xy, where x is the x coordinate that you use when you cut it parallel to the YZ plane, and y is the corresponding constant value for the plane parallel to the XZ plane. Okay, you get this curve and you get a vector here. And that vector is just tangent to the curve. Maybe it's a unit tangent vector, maybe it's some other tangent vector. Okay. But you know, this curve has a equation, a formula. You just take f of x, y, and whatever your x coordinate is where you cut it, you replace x with that number, and now you just have a function of y. And it can take its derivative with respect to y and get the slope here. Okay. And that gives us a vector that's tangent, assuming you have a nicely, a well-behaved curve that has tangents at least has tangents at this point. Okay. That vector is going to be tangent. And you do the same thing here. You replace y by whatever y is in this blue plane, and you get a function of x, and you take its derivative, and you get the slope of this thing. Okay. Then you take the slope and you do, okay, for the y direction, you do j. Well, your slope is your k component divided by your j. Okay. And that's going to give you something down here. And similar here, your slope is your k component. Your k component divided by your I component. That gives you the vectors, and work out the details of that. Don't want to write it out. Don't want to say too much more, but this vector and this vector. Okay. In other words, I plus partial f with respect to x times k is I plus slope times k. Right? Okay, well, that means your run is I and your rise is the slope. Your run is 1, I is vector of magnitude 1, and your slope and your k component has magnitude partial f with respect to x. The rise divided by the run is therefore this partial derivative with respect to x divided by 1, which is just a partial with respect to x. So this thing has a slope equal to the partial with respect to x. This vector has a slope equal to the partial with respect to y. So their cross product is by dang double normal. Okay? They're both tangent, cross product is normal. That's how you get a normal vector at a point on plane, on the graph of a function of two variables. And of course, then you have a tangent plane that's normal to that normal vector. Another way of looking at it, these two vectors are in the plane. These two vectors define the tangent plane. Okay? So take their cross product, you've got the normal of the tangent plane. And these vectors are perpendicular because these planes are perpendicular. Okay. So anyhow, there's your normal vector. There's your normal vector, tangent plane. If you know the coordinates, you can get the tangent plane. And that tangent plane is in the near vicinity of this point. A good approximation to the function. Okay. Now, the bigger your second derivatives, the more quickly that approximation deteriorates as you move away from the point. If you're close enough to the point, you can use a tangent vector or tangent plane as an approximation. And that's kind of a differential approximation, and I'll get to that, but somebody's got their hand up. So I want to make sure they're not having some kind of a event. Okay, now somebody just said, wouldn't it be easier to use the gradient? Well, first of all, the gradient of a function of two variables is a vector in the plane. It's not in three-dimensional space. Now, if you make this into a level surface of a function of three variables, and you can do that, then you can use a gradient, and it's not a bad strategy under certain circumstances. Okay. Now, I'd be willing to think a little more deeply about that and go into it more. It'd be a great question. I'll probably put it in the exam and, if you don't answer it right. No, seriously, it's an excellent question to think about. Okay. But it's not going to work to find the tangent plane to this surface. And unless you go to, this is going to be easier, quicker, more direct. You have another level of abstraction when you talk about creating a function of three variables, so you can do the gradient. Okay, but it's not hard to do. So if you want me to do that, just email me your answer. Okay. I want to think through it to make sure, right? Just got to be careful. Great is what works first. Okay. Okay, well, there we have it. You tangent plane to normal of this, you got a point. You got a point and a normal vector, get the plane. We did that. Okay. Now make sure you know how to do that. Make sure you know the picture. And then I said, I should have read it, but this is a differential approximation of f. Okay. And you can say, df equals partial f with respect to x times dx plus partial f with respect to y times dy. That would be equivalent to finding a point on the plane. Okay, because everything's linear. So that's worth thinking more about. What asked me to do more about that. Draw that equivalence out. I can do that. Okay, anyhow, the directional derivative now, in the direction of u, for u as a unit vector. Actually, yeah, I didn't specify that u is a unit vector. I just said that u is in the direction of has direction. It is directed at angle theta with respect to the positive x direction. Okay. But if you use a unit vector, then it's I cosine theta plus j sine theta. And you just do that dot product with the gradient of f, fxi plus fyj dotted with I cosine theta plus j sine theta gives you this. And I think I've just said that down here. Okay. Everything's implicit. I'm not looking ahead. I'm just saying what's obvious. And usually it comes next or something I just chose not to include because it'll be on the scope. Okay. And in some cases, maybe because I was too dumb to think about it at the time. Okay, now, so that this introduces the idea of the gradient. And the gradient's direction of maximum increase. Okay, I got the right words. Direction is that of maximum increase. I was trying to read that without the word that. It wasn't making sense. But make sure I'm making sense here. Direction of is the direction that of magnitude, maximum increase. And I think we understand that. And that's really important. Okay. Yeah, 4 stars important. Okay. And magnitude is the rate of maximum increase. Okay. So you have the direction and magnitude of the rate of maximum. Direction of maximum increase and the rate. Okay, directional derivative then is del F dot U, where U is a unit vector. I didn't say how pure U was a unit vector. I was wanting to have said that when I looked at this, because I didn't look at this before. I prefer to be spontaneous, and sometimes that works, and sometimes it's a disaster. It should work here. Okay, this is detailed enough that I can't go too far off. So I wanted this to be a unit vector, but I just specified direction. Here I said it's a unit vector, and then everything I said about I cosine theta plus j sine theta dotted with that x and that percent like j makes it complete sense. It comes complete circle. Okay, not the unit circle, but a complete circle. So I've already said it all. All right. Does that make sense? That's the early part of the course. Questions? Other things you want me to talk about? Well, they might occur to you, so please let me know. Hang on. Okay, there's an oscillating circle, something that you struggle with. And it's a good topic. It's wonderful. It's in the plane of R prime and R double prime. Okay. The centripetal acceleration is V squared over R. Okay. From that, V squared over A, we don't want to use R, let A be the radius of the oscillating circle. Okay. And its magnitude is that of the perpendicular component of R double prime, which you can easily calculate. So you get the magnitude of this, there's your acceleration. So that's equal to the magnitude, it's equal to V squared over A. But V is just the magnitude of R prime. Okay. So you've got the acceleration. You've got the velocity. You calculate A. That's the radius of your osculating circle. Okay. Now, that just means from this point, you go A units in the direction of your perpendicular component. Right there is the center of your oscillating circle, so that this curve matches the oscillating circle in the near vicinity of this point. Okay. If you want to calculate it, well, you just multiply your R double prime. Well, take your R double prime perpendicular and multiply it by whatever you need to multiply it by, so that its magnitude becomes A that you calculated from this other stuff. Okay. As I said, I haven't written it out. So you have to parse a lot of words. But that's the idea. You just go that far along this thing. And you just follow that vector. That gives you the point. So now you've got the point at the center of the circle and the radius in the plane of the circle. So you can write out the equation of the circle, which is a little bit of work. But I want to write that out. I can't wave my hands. Give you a good description of how to do that. Okay. Yeah. But you parameterize it. I mean, you can parameterize a circle. Can you parameterize a circle of given radius in a given plane with a given center? Probably had to do it in the last week. Okay. Whether you know it or not. Great foundation. Okay, so now we get into the idea of conservative fields. What's the big deal about conservative fields? Well, first of all, the integral between one point and another on a conservative field is path independent. That's a big deal. It's like a generalization of fundamental theorem for integral. Okay, you just subtract the value here, the value of the antiderivative here. Yeah, sorry, the value of the antiderivative here where you start from the value of the antiderivative where you end, and you have the integral for function of one variable. Okay, here you're in space. Okay, you just take the value of your vector function here, the value of the vector function here, do this one minus this one. It tells you what the integral is from here to here along any darn path you want to choose. As a similar thing, you know, Stokes theorem. Okay, you can take any curve, take that osculating circle if you want, and integrate a vector function around, you know, integrate the tangential component of the vector function around that circle. It's equal to the integral of the normal component of the curl over any surface that circle bounds. Okay, let's look at the right words. Any surface. Well, one of the surface could just be the flat surface. Okay, another surface might be the cylindrical surface between here and the plane. Another surface might be hemispherical surface or parabolic surface, which looks something like a hemisphere would do with your hands, rotates differently. Okay, you find a surface over which that curl function is easy to integrate, if possible, but that's not always possible. You find any darn surface you want in the whole universe, as long as it's bounded by that circle, and you can integrate circulation around that circle. Okay, and that's kind of a generalization of how you do just basic, you know, with convention. Okay. So there are a whole lot of concepts around this. Anyhow, there you have it. And it's conservative if and only if it's a gradient of some scalar function. Okay, now I think I misspoke. Said, okay, you got a conservative field, okay? You're integrating the component of the field parallel to your curve at every point. And your antiderivative is basically your potential function of which your field is a gradient. So you subtract the value of the potential function here from the value of the potential function here, and that tells you the, okay, so what I said before was just another instance of, you know, brain freeze. It wasn't quite specific because I was trying to draw a bunch of parallels and I got careless. So make sure we understand that. It's the difference of your potential function is the integral of this function between 2 points. And it's f dot t function dotted with the tangent vector. Okay. Ref dot ds. Okay. And one consequence, of course, is if your initial point is the same as your final point, well, that's what a closed curve is, and the integral is 0. Okay. Just like integrating x squared from 3 to 3. Okay. Except in this case, in that case, you don't have a curve to follow because you're only in one dimension. Here you got a curve, you follow any curve that stays within the domain of the function and where the function is continuously different. Okay. Okay, so anyhow, that's true for all closed curves. If your function is conservative, then the curl is 0. We just did that, yeah, last week or the week before. Just write out the symbols for the curl of the del L. Okay. You got I JK, partial respect to X, partial respect to Y, FX, FY, Z. Okay, you work it out and all your FYs and FZs or FXYs and FYZs and everything just cancels. And it's nice and geometric the way it works with the determinant. Okay. So you just write out what this means. Any function out is fxi plus fyj plus fzk, then write out your determinant that gives you the curl and do it, and you see, yeah, everything cancels out. Okay. So yeah, did that in class. I might well ask you. Now, what's the probability that I'll ask you, given that there are about 300 things I could ask? Probably I'll ask that is somewhat higher than most of those 300 things. Odds are still probably against it, but I'd be ready for it. Okay. And there's still a very significant chance, maybe 30 or 40% chance. Maybe only 10 or 20. But you don't take a chance because it's really easy. Okay. And again, what I say here is just do del cross fxi plus fyj plus fck equals 0, write it out and everything cancels. So, you know, what's said after this, I didn't look at this, you know, I didn't know what was coming up next. It's obvious, everything is just implicit in everything else. Okay, and it's not just the way my brain works. Almost any mathematician will tell you that, including, you know, the rare ones that are smarter than I am. I mean, the majority. Okay. Anyhow, okay. A line interval. To do a line interval, what do? You parameterize your curve. You partition your interval. Make your sample point. And figure out what the line interval is on a typical interval. Integration, setting up intervals, figuring out what to integrate, always, this may be the most important thing I've said all semester. It always comes down to what happens on a single increment of your partition. You figure out what happens in a typical increment of partition, the rest just falls into your hands. And you end up integrating the thing you want and understanding what you're getting. Okay, not just hoping that I've got the right formula here, and I hope this works out, because doesn't this whole engineering project is going to explode and kill people. Okay. No. You know, learn to, and I'm not trying to tell you how to be an engineer. I just check with your engineering instructors and parse whether what I'm telling you really makes sense, because I'm not an engineer. Okay, I don't think that way. Yeah, could have, but I'm not sure how good or bad I would have been. But just understand things as intricately and as thoroughly as possible. And to understand integrals as intricately and thoroughly as possible. There are two things. One is integration technique, which you're never going to need because you're going to do it with a machine. Okay. And you're going to do most integrals ending up that you can't integrate them with integration technique anyway. So you're going to do approximations, which you need to understand much better, I think, than you do now, but I think you will, if that's important in your field. Okay. But what's the meaning of the thing? Does the meaning correspond to what it is I'm trying to build here? Okay. To the extent you can do that, I hypothesize that you're going to be more valuable in a more advanced position where you're dealing with engineers who can't do that. Okay. And there are levels of can and can't. Okay. It's a habit of thinking. Other than the mathematical necessity of it, the habit of breaking things down, partitioning them, and building up your intervals. It's a really good piece of mental gymnastics. and also very practical. Okay, well, off the soapbox here. So if you're trying to, I didn't say it, but this would be like an arc length interval. Okay, right there is what you integrate for arc length, okay? Um, so I should say like arc length interval. And this is just the rate at which your position is changing with respect to t. And you integrate it with respect to t. Why? Because you take the rate at which the thing is changing and multiply it by delta t. That gives you a delta s. I've got another mistake here because I should have magnitude sign around that. How fast you're moving, not. I've got it here. I didn't have it here. And since I use the double absolute value for the magnitude, which is standard, I don't always write it because I don't always give myself room. But there it is. Our distance is magnitude of r prime evaluated at your sample point times your time interval. And whether this is time or distance or whatever you're parameterizing in terms of, this is the rate of change with respect to this variable. And you multiply it by the change in this variable, it tells you how far you go. All right. Well, that'd be your total arc length. I finally mentioned arc length down here. I've never mentioned it up here, but there's your arc length. Okay. If you want to find mass, you multiply by mass density. You evaluate your mass density up here, a row of x, y, z, right? Where you express x as a function of t, y as a function of t, z as a function of t, so rho would then end up being a function of t. Or you just leave it as rho of x, y, z. But since you're integrating with respect to t, you'd better have it in terms of t. Yeah, all I'm saying is if you multiply this distance by the average density, and I just said something stupid. I said, rho, no, I didn't. Okay, multiply this by density, you get a mass. Add up all your mass increments, you get your total mass. To get your approximate total mass, if you use delta t's, take the limit as your delta t's approach zero, and you get interval. Big deal, big deal. Okay, well, I would do it time. Okay. If you're integrating a vector function with respect to position along the curve, so ds is just your distance increment, which is just what we have here. Same thing we have here. In this case, though, your delta s is a vector. So it's x prime I plus y prime j plus z prime k instead of just magnitude of. Make sure you understand why. And this is your f of ti star dot delta s, which is the discrete form of what you're going to be integrating. It's like fi plus gj plus hk dotted then with x prime I plus y prime j. It gives this, you get this mess. Okay. Now, your f is your I component of your vector function, g is your j component, h is your k component, and f, g, and h are all functions of x, y, and z. They're functions of position in space. So if we write it out in all its glory, this fi plus gj plus hk would be f of x of t, y of t, z of t, because you're parameterizing in terms of t. Now, f is a function of x, y, z. So you just replace x, y, whatever your x of t function is. Same with y, same with c. So this is just some function of t now. times I, similarly for the G function, similarly for the H function. And you dot that with this and integrate it with respect to T. Okay. So you basically just get your F function times your X prime. And your Y function, which would be your G of T function times your Y. Try to interpret that geometrically, it's very illustrative. Okay. Now we look at coordinate systems, rectangular coordinate system. I think I wrote this down after I wrote this, so let's go up here. Coordinate systems and volume increments. Just a quick review. You should be able to draw these, so just kind of the way I drew this. I didn't have room here to draw the increments for cylindrical or spherical coordinates, but you should be able to draw those. I know when I took the course, I drew them dozens of times. Keep reminding myself of what I was doing until it finally sunk in my feeble brain. Okay. Anyhow, there's your volume increment. There's your volume increment. And in cylindrical coordinates, you get your R delta R because of this picture. This picture, here's your delta R. And this arc distance at this point is your R delta theta. Now your R delta theta is bigger here than it is here. But this is a small increment. So you just approximate both of them by Ri prime delta theta or Ri star delta theta, where Ri star is your sample arc between here and here. And now that makes this a rectangle because these angles are all right angles. Okay. I mean, this thing makes a right angle with the arc because it's radial and that's the arc. Okay. In the limit, these angles all approach 90 degrees and you just multiply 2 dimensions. Delta R by Ri star delta theta. Okay. If you don't fully understand that, it really ought to. And then in spherical coordinates, makes it easier to understand what happens in spherical coordinates without going into detail. Right there is the volume increment. I'm sure you're used to that because you've been using it. Yeah, I'm not going to tell you in the exam. There may be a few things that I write, a few bits of information. I'll let you know what those are in advance before I post the exam. Okay. Just a few places where maybe there's a 4 pi that you're not sure what's supposed to go. I don't want you to have to screw that up. Okay. Stuff like that. But you should be able to draw the picture and do these. I'm not going to ask you to draw the picture, Ray, but might suggest you draw the picture, but yeah, tell me what the is. Okay. I wouldn't count it against you. Then okay. I figure out what that picture's for. In cylindrical coordinates, cylinders are easy, right? You know, you just parameterize your circle down here or your ellipse, you know, the cylinder, okay, or whatever your curve is. Your weird curve cylinder and just go straight up and down. But a weird curve is probably difficult in any coordinate system. But for ellipses and especially for circles centered at the origin, cylindrical boards are really much easier than other coordinate systems. Cones are pretty easy. You know, just got expanding circles in the plane, and they project higher and higher. It projects a little higher, you end up with a cone. We've actually pictured that. In spherical stairs, ice cones, ice cream cones are easy. Okay, that's like you hold your angle phi constant and rho constant. So you've got the cylinder constant phi and the top of a sphere. That's It's something you should have seen. If you want the flat top of the sphere, you're better off with a cone. But if you want a spherical top, you're better off with some, and cones, easy with symmetrical. It's okay. And rectangular solids are easy to describe. Cylinders and spheres are not too hard in rectangular coordinates. You should be able to convert an integral in one coordinate system to the integral in the other. Okay. Now we get to moment integrals. First moment increment is just okay. For a moment, you've got an axis. Okay. You want to know the moment about that axis. You take the distance from the axis to your point and multiply it by your area increment. Now that's like if you got a disk, flat disk, take your area increment times your distance. That would be your increment of the first moment. If it's a volume increment, well, then it's this distance times your volume increment. And if it's up in mass, you multiply it by your density. Okay. And you learn how hard it is to get this thing to rotate. Moments are also important in probability. First moment related to standard deviation, stuff like that. Okay. And you think torque. Okay, second moment, you just square your distance. And if you know physics, think the moment of inertia. Okay, the moment of inertia is the second moment. There's this thing, I think, kurtosis in statistics. It's a second one. And I've always bypassed the opportunity to teach statistics. If it was being taught at a higher level, I'd love to do it. But when you're just teaching people how to use computers and formulas, I'm not interested. If I had to teach it, I would, and I'd do it enthusiastically, but I would teach stuff where you really have substance. And there's plenty of substance in statistics, a different way of thinking. Probably would be a good for me to teach it. I'll read statistics. Yeah, okay, now I know the mathematics of it. You can't talk about the mathematics of it in an introductory statistics class. So, never taught it. And I don't know that I never really took a rigorous course. So I'm a little bit ignorant of statistics, but I know the foundations real well. It's basically all this. Okay, anyhow, if you got a density, you multiply by the density. And I said that up here, and obviously that's the next thing that comes. Okay. Does that make sense? Now, those integrals are really important. You did them. Functions of single variable a year ago. Calculus 2. If you took as much. Whenever you took calculus. So you should really understand it there. You should probably review that and make sure you understand how it extends into three dimensions. Okay. And that's pretty much what you need to know about integration. Of course, you have to know a little integration technique. That's part of your. It's probably last time you're going to have to really use integration technique. And it's important. Okay. It gives you can get insight into the geometry from the integration techniques and other things too that I'm probably not thinking about right now. Okay. They also have the stuff we've done recently, but you know, there's line integrals here. Okay. And surface integrals, which I haven't talked about since that's been maybe the primary thing you've had to focus on for the last 3 weeks. Okay. So, you know, how do you do a surface integral? You parameterize. Okay. Do that RU cross RV thing, get your area increment. And looking at your scores on the recent assignments, I got to assume you're pretty good at that. Okay. Uh, Now, if you are, the time to email me, okay? Uh, because you've seen the last couple of weeks, every time I do one of these, I screw something up, I forget to copy something, and then I get confused. And, yeah, it's just, it might be an after effect of whatever that episode was in March. Talked a little too much for 2 weeks and slept 15 hours a day. Should be over that, but we're in allergy season, so I don't know. And could be just that I'm getting sent out faster than I usually do. Yeah, that's certainly a possibility. I don't think that's it. They'll keep testing to see. Because when that happens, I need to walk away from this. Okay. Any questions? I mean, I'm sure there are questions, but probably somebody would have trouble sorting them out. Okay, let me just make sure that board's focused. Looks really blurry. Okay. I can see the eyeballs of the person peeking over the top of this little person. Okay. Taking this example that I keep screwing up, although what I've got here I think is valid. Okay, it's just looking at an overview of what we're doing. We've got the intersection of two surfaces. One of them happens to be a plane, which is kind of nice. The other is a sphere, which is pretty easy. Okay, so it's fairly easy to visualize. Now, there's some weird quadratic surface with some other quadratic surface. You can imagine that even at that level, you get a pretty convoluted curve. Okay, or you could. But in this case, curves are simple. You've got a sphere being cut like this. Okay, what do? You eliminate a variable and you get your curve. So you eliminate a variable and right here's your curve. Now, as I commented last time, and then of course the curve simplifies here. And we've got a +1 = 1, so it's really all equal to 0. And you can complete the square and do all kinds of things with this, but you got that x, y in there, so you got a rotation. Okay. Which means that your intersection with the sphere, planes like out here, and your x, y axes are here. So your intersection is above an ellipse down in the XY plane that's rotated 45 degrees. And you don't get that 45-degree rotation unless you're pretty good at dealing with rotations, rotation matrices, cosine theta, negative sine theta, cosine theta, the inverse cosine theta, sine theta, negative sine theta, cosine theta. Okay? I think that's the inverse. Negative from that. Okay. That's it. Okay. Anyhow, point is, you eliminate a variable, you get the curve. Whether you can deal with that curve or not, that depends. That's a curve I wouldn't expect you to deal with, although I'd be impressed. That's something we did at this point. Okay. Now, same sphere, we do the plane. Instead of having the plane come at us like this, it's in the parallel to the line in the XZ plane from 100 to 001. Okay. And that would be this. It simplifies and you don't get that XY curve. So now you complete the square and you do everything. You deal with the curve and you realize that in the XY plane, your curve lies above the points on this ellipse. Okay. And if you think about where the circle on the ellipse is, yeah. No. Halfway from here to here, you got a circle whose radius is square root of 2 over 2. And that comes right out of this. One of the dimensions. Okay. Now, where do I go with that? I don't know. I've got the other side of this board where I'm doing something different. Or maybe it's the same problem. Because I think that maybe is the same function, but I don't know that I have the function written. So I guess I bits and pieces of things, but still, we can talk about what goes on. And up back here, you know, what go on. If I want to set out the integral over the curve of intersection, I've got to include the z coordinate. This is the shadow down in the x, y side. Well, the z coordinate is 1 minus s. Okay. So you can parameterize it. You can let parameterize this. If this was the origin, then you have square root of 2 over 4 cosine t plus 1/4 sine t. No, plus 1/2 sine. No, yeah, 1/2 sine t. Okay. And that would be a parameterization down here. Then up here, z is 1 minus x. So if x is 1/2 cosine t, then z is 1 minus 1/2 cosine t. And then you have a parameterization of the curve in 3 dimensions. Now I'm a little hesitant on the details of that curve. Okay, I think I probably said something wrong in there. If I write it out, check it out. You get it right. Okay, to parameterize this curve, you would just think of how do you parameterize an ellipse when it's centered at the origin. Okay, and then you just transform that over half a unit. And you had to ask yourself, what's the semi-axis here? What's the semi-axis here? Those are your coefficients, the cosine and the sine and all that stuff. And so that's the rest of the mechanics. You parameterize the curve in terms of whatever. Okay. And in that case, once your curve would be described as theta goes from 0 to 5. Over here, doing the, yeah, I think this is a different situation. Remember, you get your area increment by Rx cross Ry, dy, dx. In general, Ru cross Rv, du, dv. That's always going to be your area increment in the surface. Okay, you've done a lot of that. I hope. If you haven't, I'm not that optimistic about the way you did it. Okay. And then your integral of f dot ds. The mistake I made here, that integral right here, right? Perfectly good integral. And down here I wrote just what I have here, except they write the minus x over 2. So that was there. Okay. Right away, I was dead in the water as far as getting things to agree. This surface integral should have been equal to the integral around the curve or the volume increment if I was doing a divergence there. Okay. Yeah, I think this is a divergence. But there's nothing mysterious about the way this works. This is a kind of the key setting up your surfacing. Okay. So we're out of time. If you stick around, that's fine. You got better things to do, like go recover your sanity or whatever. Feel free.